Hello, welcome back to our YouTube channel, my dear friends. Welcome back to our YouTube channel, ADC Max. I'm going to apply the Parseval's identity. Already we know the Parseval's identity for the Laplace transforms, even the Fourier series. Remember, Fourier series Parseval's identity is the connection between the Fourier coefficients and the root mean square value. But what is the Parseval's identity for the complex Fourier transform? We have seen that. And also, what is the Fourier sine and cosine transform? So, what is the Parseval's identity for the Fourier sine and cosine transforms? What is the Parseval's identity for Fourier sine and cosine transform? So, Parseval's identity for Fourier sine transform is equal to integral 0 to infinity modulus of f of x to the whole square ds is equal to integral 0 to infinity modulus of f of x to the whole square dx. So this is the Parseval's identity for the Fourier sine transform. For the cosine transform, 0 to infinity modulus of Fourier cosine transform of f of x to the whole square ds, because s is the input, that is a variable. Here the left hand side, x is the variable. So x is the variable. So whatever the question is given to you, once we have the square terms, then better we can apply the Parseval's identity. So what is the application of this Parseval's identity? Yes, I can go for the application now. This is the problem. Obtain the following integrals or find the following values. The first one, integral 0 to infinity x squared by x squared plus a squared to the whole square dx, where a is the positive constant. And second one, integral 0 to infinity dx by x squared plus a squared to the whole square. That's it. Yeah, obtain the following indefinite integral values: 0 to infinity x squared by x squared plus a to the whole square, and dx by x squared plus a squared to the whole square. So something variables present in the numerator, somewhat is not there. So the better idea, if you think about the Parseval's identity, because square. So when we use the sine transform, when we use the cosine transform, as I told you that once suppose say for your sine transform of minus ax, it means that the numerator is s, the variable. So here the variable is s. So you can apply the Fourier sine transform. When you make the square, this becomes x square. Here s is the variable, here x is the variable. That's it. And for this one, we apply the Fourier cosine transform. So for this we use the Fourier cosine transform. For this we use the Fourier sine transform. Parseval's identity for the Fourier sine transform. For this, for the cosine transform. So it doesn't mention anywhere in the question paper using the Fourier transform. Evaluate it. That's it. So here what I am going to consider, I am going to consider the f of x is equal to minus ax. Yes, right? And also we know that the Fourier sine transform into minus ax equal to root 2 by pi s by x squared plus a squared. Right? So the first question, I go for the Parseval's identity for the Fourier sine transform by the Parseval's identity. By the Parseval's identity for Fourier sine transform. For Fourier sine transform. By Parseval's identity for the Fourier sine transform. Yeah, integral 0 to infinity. What is the Fourier sine transform of minus ax into ds? It's modulus of the square. ds, so integral 0 to infinity e to the power minus ax, the modulus to the whole square dx. Yeah, we can substitute e power ax as a f of x. As already we know that Fourier sine transform of the power minus ax equal to square root of 2 by pi s by s squared plus a squared. Now whole square by the Parseval's identity into ds is equal to integral 0 to infinity. The modulus of a square is always the even function, and it is e to the power minus 2ax into dx. Because by law of indices a power m power n is nothing but a power m into n. So e to the power minus ax into 2 e power minus 2ax. Now when we square this one, we get root 2 by pi whole square is 2 by pi integral 0 to infinity s squared by s squared plus a squared to the whole square into ds. I think we almost reached the answer. Here x is the variable, here s is the variable. That's it. So is equal to What about the right hand side? Right hand side is e to the power minus 2ax by minus 2a. Yeah. The limit x equal to 0 to infinity. When we substitute x is equal to infinity, we get 0 because e power minus infinity is 0. By putting x equal to 0, we get it is 1. E power minus 1 is 1. So it is minus of minus 1 by 2a. So the answer is 1 by 2a in the right hand side. So what about the question? The question is in terms of x. So can you replace x by s? Can we replace s by the variable x? We get integral 0 to infinity x squared by x squared plus a squared to the 4 squared dx is equal to, I think only 1 by 2a is there. Now this 2 by pi make the reciprocal, this becomes pi by 4a. That's it. Where a is a positive constant. Very simple concept. So what's the answer for this one? For this the answer is pi by 4a. Right? This is one of the long answer question. This is a long answer question. Please kindly say that. If it's a long answer question, you please kindly derive this part. You can kindly derive it for a sine transform to the minus ax. Here I just quote the value, but it's a long answer question. Please kindly derive the value as well, because already here I did the same. Please go and watch the previous videos. I did the separate video to evaluate the Fourier sine to cosine transform of e to the power minus ax. Please go and watch it. Okay. Now, what is the second one? So here I am going to use the sine transform because of the x in the numerator. That is the variable in the numerator. So there are no variable in the numerator, so better we can apply the cosine transform. So the same idea, I am going to use the cosine transform. So the second part, I am going to use the cosine transform. So I am going to use the cosine transform. So what happened? I use the cosine transform. So this is a cosine transform, yes, correct? So cosine transform, there is no variable, it is only the constant a in the numerator. It's clear? Is right? So there is no s squared here, it's 1 only, but this a squared becomes outside. So a squared. Clear? What about the right hand side? Right hand side is there is no change in the right hand side because the function is the same, e power minus ax only. So the right hand side is 1 by 2a, so there is no change in the right hand side. But on the left hand side, it becomes 2a squared. So when you replace x by x, we get it is 1 by x squared plus a squared whole square dx is equal to this 2a squared, make it reciprocal, pi by 2a. Here 2a squared, so 4a cubed. So the answer is here pi by 4a cubed, where a is a positive constant. So see the slight difference when it makes a huge difference. A slight difference will make a huge difference. Suppose if you know this technique, you will get the answer just like a fraction of second, you will get the answer. Suppose the questions in the competitive exams like what will be the value of integral 0 to infinity x squared by x squared plus 4 whole square dx. Very simple. So a squared equal to 4, so a equal to 2. A equal to 2 means this is pi by 4 into 2, so 4 into 2 times it's pi by 8. See, very simple concepts. But you should really apply those ideas when you are getting familiarity in the concepts. So this can be done even any other methods, by convolution theorem, even by the contour integration methods, we can do it. But which one is very comfortable, which one is very easiest to one. When you are going to attempt any competitive exams or comprehensive exams, then there is no descriptive type questions. This is only like a multiple choice questions, so that time is really help you to get this type of questions can be easily answered. Right? And what about the answer? Can you check, tell me what is the integral 0 to infinity dx by x squared plus 1 whole square. Yeah, I think the same idea. Here a equal to 1, here a equal to 1, so dx by x plus a to the whole square. So a equal to 1, so a equal to 1, that's it's pi by 4. So simply within a fraction of second, we will get the answer. Got it? So that is the real application of the Fourier transform. Because you may think that why we need to learn this types of transforms. So this is like a mathematical tool, you know. If you know the different types of tools, then if you feel which one is comfortable to you, you can use it. There's available tools here. You are going to solve the problem, the differential equations or integral equations or the difference equations even. There are a lot of techniques out there to solve a single problem, more than one method we have. But among the methods, which one is very familiar, which one is very comfortable, which one is time consuming, which one is we get a very quicker way, which one is give the more accurate value, so better can choose that concept, that techniques there is the smart idea. So because in the MCQ type questions, there are 250 questions within you have to answer 90 minutes duration. And that time you can do by this, by taking the paper, doing the rough works, it will take time. So this time consuming as well. So if you know these techniques, you need to just remember, you can apply the corresponding constants, you can get the answer just a fraction of a second. So there is a real application of this type of transforms. So even though not only this, we have the same kind of infinite integrals with the help of beta and gamma function. Yes, right? Beta and gamma function, I made a separate video, please go and watch it. Because beta and gamma function is also another easiest tool to evaluate this type of indefinite integrals. That's very important. This type of indefinite, because of here I am going to use the Parseval's and for Fourier transform. So if you know the Fourier transform, you can get these ideas. Otherwise, you won't be able to get. But beta gamma function, no transform required. You can get the answer just like that once if you familiar and apply the beta and gamma functions. Thank you so much for watching our YouTube channel. Please kindly subscribe, follow, and also recommend to your friends so that they also got benefited. That's my saying. Okay. Thank you so much for watching our YouTube channel. Signing off, your ADC Max. Thank you so much.